Okay, so here we are, more than halfway through the topics now. Hopefully you have a solid understanding of serology and you're ready to move on to a discussion of blood pattern analysis. So the first thing we should probably do is define blood stain pattern analysis, or BPA as we'll commonly refer to it this chapter. So it's the examination and analysis of blood stains left behind at a crime scene and the interpretation of how the stains were produced. Because it involves the chemistry, biology, and mathematics, physics and mathematics of the act of producing the blood stain, we'll obviously be looking at trigonometry, geometry, biology, chemistry, and physics here in this chapter. So we'll try to keep it at an appropriate level. I know a number of you are non-majors and probably are anxious enough about the math and science in the course, so we'll keep it appropriate. Those who are science majors will just get to have a little taste of what might go on, but the rest of us can rest assured that we won't be pushed too far behind our comfort zone. Now, when blood stains are part of the physical evidence found at a scene, that leads to a number of questions, of course. So we'll just list them in order here. Which direction did the blood come from? And be careful, there may be some misconceptions about what that tail has to mean. At what angle did the blood drop hit the surface? So we'll look at, again, a little bit of trigonometry there. Where was the victim and the suspect located relative to one another? How many blows did the victim receive, and from what direction did they receive them? What caused the wounds on the victim's body? So we'll be looking for the particular object in that case. What movements were made after the wounds were inflicted, right, when the blood was likely to be spattered as a result of whatever caused the wounds that allowed the blood to escape. And then how many suspects were there? Did this look like a single suspect scenario, or were there multiple suspects? Again, if we find blood of suspects, then we assume that our victim got in at least some defensive wounds, and then we'll have even more to consider as we look at blood stains that might be suspect and victim blood stains. So before we move any further, let's consider some blood stain basics. So blood spatter is the scattering of blood stains that vary in size and may be produced in numerous methods. And then on the right, we see in our picture also the area of convergence. This is the area from which the blood originated. So if we take a look here, we see a number of blood stains on the floor. And if we take each of those stain starting points and draw through, we notice that there's what's known as an area of convergence. We'll talk a little bit more about that in the next slide, but we see that tracing back each of those stains, we can see a point of convergence there that gives us an idea of where that blood stain got produced. And following up on what we just discussed, how we determine that area of convergence. So you would draw a line lengthwise through the center of each of those drops, and then the area where all the lines intersect is the height at which the blood originated. So you can have an idea of how high the victim or suspect, whichever blood stain we're considering, how high up they were when the blood spatter originated. So it's an area of convergence more than a point of convergence. Notice there's not necessarily all the lines going through a single point, but pretty close together there, and that's what we would call the area of convergence for our blood stain. Continuing with our basic definitions, we have here parent drop. That's the large drop to the right of our slide. And that's the original drop that hits the surface. Notice on that parent drop we have some spines. Spines are the pointed edges that radiate outward from the original stain, but there's still a link to it. Again, the spine that we show is particularly long, but it still trails back to that original parent drop. And then finally, we also have in this case a satellite, a fairly large satellite pointed out there that is spattered that becomes dislodged from the original parent drop. So again, though you won't always find the satellites, that just shows us that this particular blood drop, the parent drop, hit with either a particularly strong angle or force that allowed for that satellite to become dislodged. Again, the satellite's not its own separate blood drop. It's from that parent blood drop that it got dislodged. So hopefully that helps to get at least some basic terminology down for our further discussion of bloodstains. When considering bloodstains, you also have to consider the surface. So the target surface is the surface where that stain lands, and it can impart characteristics on a bloodstain. So in the first case, if we think about a solid and impermeable surface, then we're going to have less spatter found because the blood has significant surface tension, so that's going to keep the blood together, such that if we have a metal or glass surface, then we're much more likely to find a drop that's intact and together, like we see at the bottom center there of our different blood type surfaces. The smooth glass surface in particular we think of as impermeable. So that's going to give rise to a much smoother appearance of a blood stain, and a blood stain that will take much longer to dry because it sticks together. If we could contrast that with a permeable surface, now you're going to have a much greater amount of spatter because the blood will fill in the holes of that porous surface, then expel back to create the spatter. We've got some examples: cardboard, clothing, bed sheets, linoleum. So we see up in the top images the linoleum surface on the left and the cardboard surface on the right. You can definitely see those spines in that cardboard surface. If you look really closely at the top, you might even see some satellites there from some of those, whereas at the smooth glass surface, the blood drop stays together by and large, instead of having the classic spatter appearance of the linoleum or cardboard. There's also a video down at the bottom. I encourage you to click that link and watch that video that shows how surface texture affects blood stains. If we consider the height at which the blood was produced and how far it fell to reach the surface, well, if the blood drop started close to the surface, it's going to lead to a relatively small stain. If it was further from the target surface, then we would expect a larger stain. Again, this is not a challenge. If we look at that image, this sort of thing has been studied. There's no need for you to lose any of your blood testing this theory. We want to keep our blood inside our bodies because we need it for all the reasons we talked about back in serology. So suffice it to say, the testing here that we show, you can see a 6-inch blood drop, height of the drop anyway, for 6 inches from the surface gives a much smaller blood stain than for the 7 foot from the surface drop. So we don't give particular values there, it's all relative, but again, the rule is the diameter of the blood stain increases as the height increases between the source of the blood stain and the surface of the stain. Okay, so now we get into an area where there's a number of misconceptions out there. So if we look here at the direction of travel, a lot of people think that that little tail at the end is propelling that blood forward, sort of like the tail of sperm, causing the sperm to swim away from it. In actuality, the tail gives you the direction of the travel. So in this case, that blood is traveling, say, northwest, because that's where we see the tail, again, assuming that north is straight up on the slide and west is over to the left. So whereas some people may have been under the misconception that that blood stain's traveling from tail to head, it's actually quite the opposite. The tail, that smaller stain part up at the top, is actually imparting in us the direction of the stain. So be careful about that. The tail of the blood points in the direction of the travel, not the larger head part that you might expect. So keep that in mind. It's going to be important, particularly as we consider our exam for this topic. Now let's consider the angle of impact. If the blood drop falls at a 90-degree angle, then we'd expect a perfect circle. Of course, there's no such thing as a perfect circle, but we're going to get a much more circular blood drop at 90 degrees than for lower angles. So if we're less than 90 degrees, we're going to get more elliptical in shape. So if you look at the 80-degree image there on our picture to the right, we can see it's much more elliptical, and 70 even more so, 60 quite elliptical, but then as we go down to 40, 20, 10, we see much more elongated shapes, and we're also far more likely to have tails or spines that drip downward as we get to those really low angle stains. So if you would like to see how this angle impacts a blood stain, there's a nice video there for you to click and watch, and hopefully that will make much more sense if you're struggling with it just from looking at this picture here and my description. So please do watch the video and reach out if there's still questions, if you're still struggling with it. But again, if you're at 90 degrees, we expect a very circular blood stain. If you're at lower angle, we expect a more elliptical shape, and if you get down to really low angle, then we're looking at, again, excessive tails and spines and such. So please do watch that other video and reach out if you still need more guidance. Now that we know how to predict from the appearance of the blood stain the relative angle from 90 to lower angles, we could actually calculate that angle of impact if we were to measure the blood stain. So we measure the width and length in millimeters, we divide the width by the length, and then on your calculator you'll hit arc sine or inverse sine, as you may have learned it. So it's the shift or the second button, and then the normal sine, by hitting shift or second, that turns it into the inverse sine or arc sine, and you'll round that number that you get to the nearest whole number. So that's how you can actually determine the angle of impact rather than just give a relative value, whether it was close to 90 or much lower than 90 based on the appearance. We can find the actual number if we're willing to do a little bit of math here. Now let's consider a specific example. So if we're calculating the angle of impact for a stain that's 15 millimeters wide and 35 millimeters long, well, we'll divide the width by the length. Again, the length should be a larger value, the width should be a relatively smaller value, so we should end up with a ratio of width divided by length that's less than 1. So here we get 0.42857. So if we take the arc sine or the inverse sine, right, the second and sine button in that order, right, make sure you hit the second first or you'll just get the regular sine, which won't give you the correct answer. But if you do it correctly, and this is a good way to check yourself and make sure that you're doing it correctly, you should end up with a value of 25.37693 or something very, very close. Again, those last few digits may differ depending on your calculator, but when you round your number to the nearest whole number, you should get 25 degrees. If you get anything else, then try again. Make sure that you've hit the second or shift button before you hit the sine. Make sure that it's taking the arc sine or inverse sine of the 0.42857 value. If you're not sure why it's not giving a final answer of 25 degrees, please do reach out and just let me know what answer you're getting so that we can figure out where you may be making a mistake there. Okay, but hopefully if you did everything correctly, you arrived at the same answer and we're good to calculate the angle of impact for a blood stain. Earlier we looked at the area of convergence. Now we can look at the area, or sometimes point, of origin. Again, it's not really like you get a very fine specific point, so area is probably a better term, but you'll see it referred to as both the area and the point of origin depending on where you look. So in order to find this value, you'll calculate those impact angles for each drop, and we just talked about how to do that. A string would be attached to each drop and placed on a pole with the correct angle so that it's being traced back to its source. And then finally, the area where all of those strings intersect would be the area or point of origin. So again, it relies on multiple iterations of that equation that we just looked at together, where we took that arc sine of the stains width divided by length, and you'll do that for each of the individual blood drops from the blood stain, and if you did that correctly, you'll end up with the point of origin for that blood drop. So not just the height like we got with the area of convergence, but the actual three-dimensional point where the victim or suspect, whatever blood stains we're following at this point, where they were and where that blood originated from. So very powerful thing, and again, another video down there at the bottom for you to watch if you're still looking to have a better explanation of this topic. But hopefully it makes sense, and if it doesn't make sense even after the video, please do reach out and I'll try my best to make sure it makes sense to you. So with a little better background on blood stains in general, let's talk about the different types of blood stains. And the four major types that we'll discuss here are passive, transfer, projected, and impact stains. And we'll talk about each one of these in turn, so don't worry if you're not sure what they mean. We'll take them one by one, and hopefully you'll have a much better understanding after that. So the first type that we'll discuss are the passive blood stains, and these are simply caused by gravity. So the person's been injured, their blood is coming out, but it's not under any particular force other than gravity. So the gravity is determining how the blood drips, and so we're likely to see drip stains, drip patterns, drip trail patterns that are consistent with just the action of gravity on the blood as it exits the body. If there's a significant hole, particularly say an artery or something is severed, we could have a flow. If there's again a non-porous surface, you're likely to get pooling of the blood. If it's a porous surface, you're more likely to see a saturation stain. Again, that's just the large amounts of blood will interact differently with a non-porous surface to form a pool versus a porous surface where they can soak in and form a saturation type stain. So hopefully that's a little better understanding of that first type, the passive blood stain. So here we see one of those passive drip stains. So it's caused, again, like any passive stain, by falling drop due to gravity. If the drop's falling at 90 degrees or very close to it, then the spines may or may not appear depending on the surface. If the spines are attached to the parent drops, they're going to be very evenly sized and evenly dispersed in a passive drip stain. Okay, so that's what we would look for. Again, they're quite circular in appearance if they're close to that 90-degree angle of fall. Because we're dealing with these passive stains and gravity's the main effect there, you're likely, if the person has been injured to the point where much blood comes out, then you're going to get the drips to fall one on top of another, and so you'll have that original parent drop that may look more like the last pattern for that passive drip stain. But if more drops fall on it, then what you expect to see are the satellites. So before we saw some spines, but not much else. Now we see satellites because each drop that falls on the parent drop propels those satellites forward. And so the more drops that fall, the more satellites that will be created. And again, the better indication that the person had their blood dripping for quite a while on that same spot due to gravity in a passive drip pattern. Alright, so now looking at the passive drip trail, again, there's no additional force propelling the drops downward aside from gravity, so that's why they're passive drips here, but there is generally movement indicated. So this is a drop coming from a weapon or a person or a bloody site on the victim, for instance, and it leaves a trail indicating movement of either the weapon, the suspect, or the victim, depending on whose blood it is and where the blood's coming from. So the nice thing about the passive drip trail is that you can get some information about the direction of that movement. So we're not looking at perfect circular drops anymore because there's three-dimensional movement of the source of the drip, we're going to be able to see that there's more spines on one side of the parent drop relative to the other. So the side with the more excessive drops, if we look at our picture here, the spines there are more on the right side, which indicates if we define north as straight up like the image has there, the person is moving from east to west. That's why the spines are more prevalent if pointing in the east direction. That's the indication that our suspect or victim or whoever gave rise to these passive drip trails is moving to the west, and that's why there are fewer spines on that western direction of the drop and more on the east. So the greater number of spines is the area that the person is moving from, and the fewer number of spines is where they're moving to. So the passive drip trail gives us that extra information. And we can also have a passive flow pattern if there's a significant amount of blood and it contacts the surface at a higher level, and then the blood moves downward due to gravity. We can see here that we've got a flow pattern where the blood struck this particular surface up higher and then flowed down to a lower point due to that gravitational attraction. So that gives us a pretty good indication of where the spatter originally hit, which is significantly higher than where the majority of that blood in the droplet has pooled due to gravity's action. Now on to passive pools of blood. Again, a pool would be accumulation of blood in one area on a flat surface. Again, a significant amount of blood as we see here in our image. And if it's a non-absorbent surface like we see, it's going to take a long time for that blood stain to dry, and so it's going to stay as a pool of blood for quite a while because the blood itself is staying together, and it takes a while for the blood pool to evaporate its water content and become a dried blood stain. And here we see a passive saturation stain, which is similar to the pool, so it probably formed from a pool of blood, but whereas the previous slide had the pool of blood on a non-absorbent surface, a saturation stain is a pool that forms on an absorbent surface and then is absorbed into that surface. Because of the action of the absorption on that absorbent surface, you're going to get an appearance of the saturation stain that's probably larger than the original blood pool would have been, because the pool is kind of pulled by capillary action out and away, and that gives it a larger appearance than if the blood had pooled on a non-absorbent surface. So that's the biggest distinction between a pool of blood and a saturation stain formed from the pool of blood is the type of surface that it happened to fall on. If it was a non-absorbent surface, then it's likely to stay a pool for much longer, and even when it evaporates, it's still going to have the pooling characteristics, whereas on an absorbent surface, it's going to be wicked away a bit out in a way to give a larger appearance stain that's going to dry much faster. Alright, so now let's consider transfer stains. These are created when a bloody object comes into contact with another surface. They tend to start dark and will become lighter in color. And some examples would be wipes or swipes of blood, patterns like a bloody handprint or a bloody shoe print. So these are transfer stains where that bloody object transfers the blood onto another surface. So looking at an example of a transfer stain, we have wipes. So a blood wipe is created when an object moves through a bloody surface. So if the suspect starts to clean up the blood and then panics or realizes there's not enough time and has to leave quickly and doesn't finish the job, so the blood wipe will create that characteristic appearance. If the blood has started to dry and then it's wiped again, you'll get what's known as either skeletonized or perimeter stains, where there's the original dried stain as we see here, and then a wipe through it that doesn't quite destroy that original stain. The perimeter stain or the skeletonized stain is the original stain plus the wipe through stain that we can see here. Now, opposed to wipes, we can also have swipes as a type of transfer stain. And so a swipe is created when a bloody object contacts a non-bloody surface. And so you'll usually have a heavier side of blood showing the direction of motion. So in this case, if we again assume north is straight up and east is to the right, then we have a more significant blood on the left or west side and less on the east side. So this is a swipe that was from west to east. And that's why we have more blood where the bloody object first contacted the non-bloody surface, and then less blood as it moved along that surface from west to east. Of course, it's never good to have blood stains because that indicates that there's been some pretty violent activity. But one of the fortunate things of a transfer stain is that you might be able to get some patterns out of it. So if we look here, we have a shoe print that we can see based on the transfer stain of the bloody shoe transferring its pattern through the blood stain. And so therefore we might be able to match that shoe with a manufacturer, with a size, with if there's particular wear. When we talk later about characteristic wear, then again, it's important that we recognize that there's additional information, not just the blood transfer itself, but the pattern that's left that could be helpful physical evidence for that particular case. So instead of considering just the passive stains that were affected mainly by gravity, or the transfer stains by wiping a bloody object along a non-bloodied surface, we finally come to projected stains. So these are different because these are caused by the blood being under pressure. So some examples here are the arterial spurts, where the pumping action of the heart actually propels that blood forward through an artery. There's expiration stain or cast-off stains, where there's additional force, not just gravity or the object swiping. So let's go ahead and look at some of these stains. So the first projected stain we'll consider is an arterial spurt. So we see a picture of that on the right-hand side of the slide, and so that's caused by blood exiting an artery under pressure. Like I just mentioned, as the heart pumps, it causes the blood to be forced through the arteries under pressure, and therefore if the artery is severed, then the blood will be pushed out of the body instead of in the body where it belongs. Because we're dealing with an arterial spurt here, we expect to see some bright red blood stain, since that blood that's being pushed through the arteries has been oxygenated in the lungs. It's going to be particularly bright red, and we'll also see that we tend to have some significant drip patterns there if you take a look at the picture, because there's usually a lot of blood since it's forced out through the pressure of the heart beating. Now, if we consider our second type of projected stain, an expiration stain, this is caused by air forcing the blood out of the nose, mouth, or a wound area. So because you've got the air involved, you're going to get high pressure mist-like drips that are going to be visible as small blood droplets. Under low pressure, you're going to get larger stains with longer tails. So depending on how much pressure, how much force of air moving through and causing that expiration stain, if it's a higher pressure situation, you're going to get the smaller mist. If it's a lower pressure situation, you're going to expect larger stains with longer tails. So that'll give you some information about how much air was forcing that blood out of that particular nose, mouth, or wound area. And the last type of projected stain we'll consider are the cast-off stains. So this is blood drops released from an object due to the object being in motion. And there will be both a forward and a backward pattern to this. So if we consider the image on the right there, you have that tool that again is initially clean. Once it's used to cause a wound, then it's going to have blood on the one surface of it. As it makes that wound, it's going to cause some forward spatter. especially if it were used multiple times. Then if it's pulled out, there'll be some cast-off stains. Those are what we're considering here, more so than the forward or backward spatter. We're looking at the stains that result from just the bloodied tool being moved with enough force to cause the blood to be cast off from the object. The particular use of cast-off stains is you'll be able to determine if the perpetrator is right or left-handed based on that backward thrust. So depending on the direction the backward thrust comes from, that will give you an indication whether this particular suspect was using his or her right or left hand based on the cast-off stain pattern. All right, and now the last type of blood stain we're going to consider is an impact spatter, and so that's created when a force is applied to the blood itself. Depends on the force applied and the speed in which it exits the body for the particular type of impact spatter we'll consider. And there's three different types, the low, medium, and high velocity impact spatters. So we'll see how they differ, and we'll define those particular velocities in the coming slides. Looking at the low velocity impact spatter, we've got a force of energy equal to gravity up to 5 feet per second. And because it's moving in such a relatively slow fashion, we're going to expect large diameter drops, so about 4 to 5 millimeter diameter drops. And again, an example would be blood dripping from a wound, or blood spatter caused by a blunt object that was not swung with particularly great force by the assailant. So looking at the image there in the top of the slide, you'll see far right we see the pattern for our low velocity impact spatter. Now moving up to medium velocity impact spatter, we've got again a force now from that low level of 5 feet per second up to about 25 feet per second. And if we look again at that image, we can see a dramatically smaller drop size from that increased force. So about 1 to 3 millimeters in diameter. And that's generally produced from beatings, stabbings, or secondary spatter of an individual who's already been injured. So that's what we would expect to see in medium velocity cases. And now finally for our last case, the high velocity impact spatter. Now we're dealing with a force of energy greater than 100 feet per second, so we sort of jumped between 25 up to 100. This is going to give rise to the smallest diameter patterns, 1 millimeter or less, or even a mist-like spray. And generally we're talking about something now produced from a gunshot or explosion, a high-speed automobile accident, something involving really high velocity impact, and that's what would give rise to that particular impact spatter. Now our last pattern that we'll discuss isn't so much its own pattern, but a missing piece of one of the other types of patterns that we've talked about, and this is called a void pattern. So a void pattern occurs when an object blocks some of the spatter from the target surface. So here on the left image we see the weapon there very neatly fits into that void pattern and explains why that particular part of the pattern is missing. We could also have a person, if there's multiple victims, for instance, one body could be blocking the blood spatter of another. So the void pattern can be particularly helpful in determining what we might be looking for in the way of a murder weapon, for instance, as we see on the left, or if there were maybe multiple victims and one body had been dragged, or some such unusual circumstance. So just because you're missing something of the pattern, oftentimes it makes for things to become more clear rather than less clear when you encounter a void pattern. And finally, we'll talk about evidence documentation and collection. Again, this is something that we've already discussed here in the course. So we know the very first thing is to secure and protect the scene, then your initial walkthrough and all of that. And so now we're finally to the stage where we're getting out the evidence markers, taking our photographs, narrating videos. In cases where blood spatter is a type of physical evidence present at the scene, you're going to want to get close-up photographs with rulers next to stains or around the perimeter of the stain to give an indication of size. If the object with the stain can be sent to the lab or cut out, we want to make sure that we allow it to air dry first. Then we place it in a paper bag, a non-airtight container, so that we don't run the risk of molds degrading the sample. Again, of course, all of the information we discussed back in the serology topic are still applicable. So just because the blood is in a spatter pattern that's going to give us additional information, it's still blood. We still will likely want to try to analyze it for DNA, and that requires us to have an intact sample that hasn't been degraded by molds, and that can be used for not only the information that the blood spatter can give, but the information that the blood itself might be capable of providing. So hopefully you've gotten a much better idea of how valuable blood pattern analysis can be, and what those different blood stains might arise from, and how we can interpret those blood stains and get additional information about what might have happened, and ultimately have some sort of method of reconstructing that particular incident. So there's software, of course, that can be invoked to help get an idea based on all of the great information that blood stain analysis can give some indication of what actually happened, and present to the jury something logical about what transpired and how that blood stain or the blood stains were generated at the scene. So hopefully this has been helpful. I look forward to talking with you again for the next topic. Take care, everybody.